All right, so today I'm going to talk about colligative properties. So the first thing you have to know is what a colligative property is. It says here it's properties that are affected by the concentration of solute particles. Something interesting about this is that it's not actually dependent on what the solute is, just the number of particles with the solute. And so something to think about here, like if you are, for instance, dissolving like sodium chloride versus potassium chloride versus magnesium oxide, all these things are going to have the same effect on your solvent. So that's what, when I say it's not dependent on the identity of the solute, that's what I mean. There are actually 4 of them that we normally talk about. One of them is freezing point depression. Another one is boiling point elevation. Those are the 2 we're going to focus on in this class. There's also osmotic pressure, which is related to osmosis. It's the amount of pressure that's exerted on a membrane when water is trying to move through it. But as I said, we won't focus on osmotic pressure. And the other one is vapor pressure. So talking about these different things, if you look at this chart, you might see that the solute, as you increase the concentration of the solute, molality, by the way, we haven't talked about that before, but molality is another type of concentration. It's moles of solute per kilograms of solvent. So as you increase the concentration here, you see that the freezing point goes down. And this is a little explanation for why that happens. If you look at this, what's happening here is the green particles, those are representing solute particles. They're getting in the way of the water when it's trying to form its hydrogen bonds, and that's making it harder for the water to freeze. And so it actually has to be colder for the water to freeze. All right. This is a sort of weird situation. So in this case, what this is it's mixing ethylene glycol, which is antifreeze, with water. And you see that what happens here is, as you start mixing in the antifreeze, the freezing point of water goes down and down and down and down. It actually gets down to negative, here it looks like negative 70 or so Fahrenheit, or about negative 57 Celsius. And it's going down because like I had said, all of those ethylene glycol particles are getting in the way of the hydrogen bonding for the water, so it makes it harder to freeze. Now, it starts going back up here, and the reason for that is actually because at this point we're mostly ethylene glycol, and we're getting closer and closer and closer to being ethylene glycol. So ethylene glycol, it has a freezing point here, you can see, of about negative 12. And so as you get closer to being pure ethylene glycol, what happens is you actually reduce the freezing point depression, because now we've got just a slight amount of water dissolved in ethylene glycol, and so it goes up there at the end. So there's this kind of perfect mixture that you get in here where the freezing point is the lowest. So some ways where we use this, the freezing point depression. So I already talked about antifreeze. It makes it so that your engine doesn't freeze in the winter, which would be really bad. Also, that calcium chloride salt that we spread on the sidewalks during the winter to melt the ice, it's because it takes the freezing point of the water and it makes it lower than it is outside. So it turns it into liquid water even though it's below the freezing point, and hopefully that liquid water then runs off or evaporates, and then there's no more ice. So now we're talking about the other side of this. We're talking about boiling. And so you see if you add solute, then the boiling temperature actually goes up. This is called boiling point elevation. The reason for this has to do with something called the vapor pressure. And in order to understand this, you have to remember that the boiling point of a substance is when its vapor pressure equals the air pressure. Basically, water, all the little particles of water are moving around, and some of them are escaping into the gas phase. There's a pressure created by the particles that are escaping into gas phase. And so what happens normally at 100 degrees Celsius is the pressure that's created by all these particles escaping the surface is equal to the atmospheric pressure, and that allows it to boil. If you put some sort of solute in there, what happens is it's going to reduce the vapor pressure, because essentially what we're doing is we're introducing other particles in there that have low vapor pressures, and so it brings the average vapor pressure down at the temperature of, say, 102, and so we have to get hotter and hotter to boil it the more solute that we have dissolved. All right, and this is just a graph here which shows you that property. So this is the vapor pressure curve for normal water. You can see that the vapor pressure is less for water when it has a solute in it. Times when we'd use these, as I said, in a radiator, again, we can use antifreeze. We don't want the radiator to have all the coolant boil away, because if the coolant boiled away, there'd be nothing left in there. And so your engine has something on it where if the pressure builds up, it just releases. The radiator cap will a valve will open up and it will start putting out the coolant, and so you don't want your coolant to boil because then the pressure will get too high and all the boiled coolant will escape, and that's problematic. So we want the antifreeze to boil at a really high temperature so that it doesn't escape your coolant system. Another example is if you want to cook pasta faster, you can add some salt to it and it will make the water boil at a higher temperature, and if the water is boiling at a higher temperature, the pasta doesn't have to cook as long. This doesn't mean that it starts boiling faster. In fact, it's going to take longer for it to boil because it has to get to a higher temperature before it starts boiling, but in the end, it still cooks your pasta faster. There's one last thing here talking about with colligative properties, and it has to do with electrolytes. And so here's the thing with electrolytes. They will break into pieces when you put them in a solution. So normally when we talk about electrolytes, we're talking about ionic solutions. And so if you have an ion as a solute, it will split apart in the water. And so what we see if something's covalent, it doesn't split apart, which actually generally means that you have less particles in solution. So here the ionic substance, we've got lots of particles. Here we don't have as many. And so if it's ionic and it's going to split into a lot of pieces, it actually ends up having more effect. And so this is something called the Van 't Hoff factor. I talk about that more in depth with the colligative property problem set. And so if you want to know more about the Van 't Hoff factor, look there. So yeah, the non-electrolytes, these are not going to split up. And again, just the definition of electrolytes. Electrolytes will conduct electricity if you put them in solution. Non-electrolytes don't. So if you think about these three things and you're wondering which one's going to be better for for melting the ice on your sidewalk, you want one that's going to split into a bunch of pieces. This one looks like it has a lot of atoms in it, and it does, but the thing is, this is glucose sugar, which is covalent, which means it's not going to split apart. Okay, so it's only one particle when you put it in there, so it's not very effective. NaCl is going to break into two pieces. CaCl2 breaks into three pieces, and so CaCl2 is going to be the best for melting ice on the sidewalk, and that's what we tend to use. All right, so that is it for the set of notes. If you have any questions, come in and ask.